Good afternoon, everybody, and welcome to this week's Heidelberg Joint Astronomical Colloquium, the penultimate of this semester. And I'm very happy to welcome today's speaker, Francesca Fragkoudi of the European Southern Observatory, who will tell us about her work on simulating the evolution of galaxies such as our own Milky Way. And I call on Francesca's host, Nadine Neumeier, to make the formal introduction.
Okay, thank you, Richard. So welcome everybody. It's my real pleasure to introduce today's colloquium speaker, Francesca Fragkoudi, who is actually currently a fellow at ESO in Garching. Francesca received her PhD in Marseille, working with Lia Athanassoula and Albert Bosma on bars in galaxies and the effect of bulges on the disks of galaxies. Then she moved to Paris, to the Observatory de Paris for her first postdoc with Paola Di Matteo and Misha Haywood. After that, she moved to MPA in Garching as a postdoctoral fellow and then continued her independent fellowship work at ESO in Garching, just across the road. So, however, Francesca won't be at ESO for so much longer, as she's just on the verge of taking up an assistant professorship at the Institute for Computational Cosmology at the University of Durham. Apart from actually doing science herself, Francesca is a very dedicated and enthusiastic science communicator and a very committed person who is in fact using astronomy as a powerful tool for inspiring and fostering a sense of global citizenship. So Francesca is herself a true citizen of the world because for her scientific career, she went across Europe. She started her undergrads in the UK, a master's in Spain, the PhD in France, fellowships in Germany, and now returning to the UK. And just after her master's, Francesca toured through South America to join the Galileo Mobile Initiative that shares astronomy education with schools around the world. It was at the time when she actually had the idea to found the now award-winning project Columba Hypatia, Astronomy for Peace, that she now coordinates. Columba uses astronomy as a tool for peace and diplomacy on the post-conflict island of Cyprus, where Francesca is originally from. In her scientific work, Francesca is particularly interested in the connection between dynamical processes in galaxies and the broader cosmological context, and in the dark matter problem. She uses theoretical tools such as isolated and cosmological n-body simulations and hydrodynamical simulations to interpret observations of the Milky Way and of galaxies in the nearby universe. So as we said, Francesca is unfortunately only visiting us virtually today, but we have already identified a period for an in-person visit, which will be May 23rd through May 25th. So at the time, we can welcome her in person to Heidelberg, and we're very much looking forward to that. So with that, I would like to hand over to Francesca, who will now tell us about barred galaxies in lambdaCDM, uncovering the formation and evolution and dark matter content of Milky Way type galaxies. Francesca, please, the floor is yours.
Thank you very much, Nadine. I hope you can all hear me well and see the slides well.
Yes.
Great. So yes, thank you very much. It's really a pleasure to be giving this talk. Thanks for having me, and thanks, Nadine, for hosting and for the very nice introduction. So today I'm going to be telling you about some of the work that we've been doing in using simulations and in particular cosmological simulations to study the dynamics of bars in the lambdaCDM cosmological context in order to try and understand more about the formation, the evolution, and the dark matter content of galaxies like our own Milky Way, which is itself a prototypical barred spiral galaxy. So I was told that there's quite a wide range of backgrounds in the audience. So I'm going to start with a very kind of broad introduction on barred galaxies, how they affect their host galaxy, what bars are, and introduce some of the concepts that I'll be talking about later in the talk. Okay, so really starting kind of at the beginning. So bars are these elongated structures that we see running through the centers of galaxies. So let me just pause this. So these are these elongated structures that we see in spiral galaxies that rotate. You see at a given angle with a given angular frequency. And bars actually form due to global instabilities in stellar disks. And what they do is they can transport angular momentum from the inner regions of the galaxy to the outer regions of the galaxy, and they can therefore bring the galaxy into a lower energy configuration. And because of this, when a galaxy can form a bar, a galaxy will actually tend to form a bar because it can redistribute angular momentum in this way. And this is why we think that quite a significant fraction of spiral galaxies in the local universe, estimates vary between half to 2/3 of them, are actually host bars. So barred galaxies make up a significant fraction of the population of spiral galaxies. And of course, they make up one arm of the well-known Hubble tuning fork diagram down here. And this also includes our own Milky Way as well. So galaxies like our own Milky Way. So if we want to understand galaxy formation evolution, we of course need to understand how bars form and evolve and how they affect their host galaxies as well. So just to give you a brief introduction to bars, what are these structures made up of? So as I said, these are stellar structures. These are elongated stellar structures that are made up of resonant orbits. And here I'm showing you some examples of resonant orbits. So these are orbits whose natural frequencies are commensurate with the angular frequency of the bars, so where the radial frequency and the azimuthal frequency of these orbits is commensurate with the angular frequency of the bar itself. And you can see here, I'm showing you 3 examples of resonant orbits in a simulation of a barred galaxy. On the left, in an inertial frame of reference, and on the right, these are these same 3 orbits, but in a frame of reference that rotates with the same angular frequency as the bar. And you can see an orbit, for example, here inside the bar region. So this is one of the bar supporting orbits. And you can see it's very elongated, and in a rotating frame of reference, it just essentially moves up and down the bar. And here you have orbits in the disk of the galaxy that are trapped in resonance with the bar. And these are actually called co-rotating orbits, and they have the same azimuthal frequency as the bar pattern, as a bar angular frequency as well. So a useful concept when we're trying to study the dynamics of bars is the concept of closed periodic orbits, like the ones I'm showing here. So as the name suggests, these are orbits that are closed and periodic, and these actually make up the backbone of stellar bars because they can trap around them non-closed orbits, ones you can see here, and that's because these are stable. And I'm showing you here examples of closed periodic orbits from 2 families of closed periodic orbits that are very important when studying barred galaxies. So these are the X1 family, which are these elongated orbits that are along the bar, and an example of a trapped orbit, X1 trapped orbit would be the one here. And these are, and also of the X2 orbits, which are aligned perpendicular to the bar. And these orbits, the X1 and X2 orbits, are 2-to-1 resonant. So they move radially inwards and outwards when they move once around the center of the galaxy. And you can represent these orbits, for example, in these kinds of diagrams where you can look at the energy. And this gives you some measure of the extent of the orbit. In this case, it would be something like where the orbit cuts the y-axis or the x-axis. And each of these orbits would be a point in this diagram, and each line is a family of these closed periodic orbits. So this line here corresponds to the X1 family, this line here corresponds to the X2 family, and so on. And so we've, when we want to try and understand how stars and gas are shaped in barred galaxies, these are very useful tools for actually understanding these. And of course, there are also, we can also use this to study orbits outside of the actual bar within the disk. And here I'm showing you some examples again of resonant orbits. These are closed periodic orbits that are trapped at the outer Lindblad resonance. So these are outer Lindblad resonant orbits. And equivalently to the orbits that I was showing you inside the bar, you have these X11 orbits, they're called, which are aligned with the bar, and the X12 orbits, which are perpendicular to the bar. This is from the nice work of Dennen et al. In 2000, And these, you can see here an example of one of these trapped orbits at OLR in the simulation of a barred spiral galaxy. Okay, so all of these kind of complex orbits and all of this, these dynamical processes that happen inside bars are what make bars one of the main drivers of the late time evolution of galaxies. And how they do this in particular, so for example, bars can create shocks in the gas on the leading edges of the bar. So these are seen as these dust lanes that we often see in barred spiral galaxies. So gas basically piles up on the leading edges of the bar, it shocks, and then it loses angular momentum, and it's forced to funnel towards the central regions of the galaxy. And there it can build up nuclear structures, such as so-called nuclear disks, which are these small rotating nuclear disks that we see in spiral galaxies. And you can have intense bursts of star formation and feedback from all this gas that's being pushed to the center. This funneling of gas to the center is very important also for building a gas reservoir for AGN activity at late times, because you need some way to bring gas to the center. You need to induce some kind of torque into the gas to remove its angular momentum and push it to the central region. So bars can do this for you at late times. And also, as I was mentioning, bars can also trap stars on orbits and resonant orbits within the disk, and so they can therefore redistribute stars within the disk as well. And bars also form these structures in the central regions of galaxies, which are called boxy peanut bulges. So I'm going to spend just a couple of minutes to explain what these boxy peanut bulges are. So a way to think about this is if you imagine a star moving around the center of the galaxy. As it moves around, it also, of course, oscillates in the vertical direction. And if the frequency with which it oscillates in the vertical direction is also commensurate with the bar frequency, then these stars can also get trapped in resonances. And in particular, an important resonance is also the 2-to-1 vertical resonance. And when a star gets trapped here, the orbits will get distorted out of the plane of the galaxy into a banana, or also called pretzel-shaped orbits. There's different types of orbits. So here what I'm going to show you now is an orbit of such an orbit. So this is now in the XZ plane, so the galaxy's edge on here. And this is from, again, from one of these simulations that I was showing you before. So you can see a star that's orbiting in the galaxy. It's originally confined quite close to the plane, but as the star gets trapped in this 2-1 vertical resonance, it gets pushed and heated out of the plane of the galaxy into these X-shaped or banana-shaped orbits. And these are what give rise to the shape of these structures, which are called boxy peanut bulges. So if we look at now an n-body simulation of a barred galaxy, you can see here, this is the face-on distribution of the disk. So this is showing you the star's face-on, and this is showing you the star's edge-on. And you can see that this galaxy forms a bar, and I'm rotating the bar always to be along the x-axis. And that's because I want you to focus on the bottom panel here. So if I just fast forward a bit, you'll see that after some time, you have this X shape or peanut shape that pops out of the plane. So this is this kind of boxy peanut bulge that bars form due to these instabilities. And these types of structures are seen in many spiral galaxies, and we also know that we have this kind of structure in the Milky Way as well. The other reason it's really interesting to study bars as well is because the formation and the properties of bars are very tightly related to the properties of the dark matter halo. So in particular, the relationship between the bar and the dark matter halo is very complex, but two kind of major things that we can often talk about is the fact that if you embed a disk galaxy inside a massive halo, you can stabilize the disk against bar formation. And the second thing is that if you embed a barred spiral galaxy inside a massive halo, you can actually slow down the speed of the bar through dynamical friction. So dynamical friction was first described by Chandrasekhar in 1933. And the idea, just to remind you, is that if you have a massive particle moving through a homogeneous sea of very low mass particles, as it moves through, these small mass particles will be attracted to the massive particle and will form a kind of wake behind the massive particle. But in turn, of course, the massive particle then feels the pull from these gravitational pull from these low mass particles. So as this moves through this sea of low mass particles, it will feel a kind of drag force or a frictional force that can slow down this particle. And you have something equivalent happening also in the case of bars that move as they move through the dark matter halo. They can get slowed down through this frictional force. The difference here is that in the case of a barred galaxy, this tends to happen. This dynamical friction is exerted essentially by near resonant particles. And here I'm showing you a video of a dark matter particle that's trapped at resonance by the bar. So this is in a rotating frame of reference, and you see the face on distribution and the edge on distributions here. And you can see how dark matter can also get trapped by these bar resonances. Okay, so I've said a little bit about bars in general. So now I'm just going to dive into how this can help us learn about the formation of the Milky Way, which is a prototypical example of a barred galaxy. So if we want to study how galaxies form, a good place to go and look is, of course, in the inner regions of galaxies, because these are the first regions to assemble. Now, when we look in the inner regions of galaxies on opposite sides of the spectrum, we see on the one hand structures called classical bulges. So these are dispersion-dominated spheroids that are thought to form through rather violent processes, such as mergers or clump migration. And on the other hand, we have these so-called pseudo-bulges, which includes things like the boxy peanuts I was mentioning, but also the nuclear disks that also form through gas being pushed to the center as well by bars. And what these have in common is that they're less concentrated than these structures on the left, and they're also thought to form through secular processes, so through disk instabilities or resonances. And of course, these very different formation processes leave different chemodynamical imprints on stellar populations in the inner regions. And so by going and modeling the chemodynamical properties of stellar populations in the bulge of the Milky Way, we can try and decipher how it formed. So just very briefly, a few words about the properties of the Milky Way bulge that we know of. So in terms of morphology and kinematics, globally, we know that the Milky Way is consistent with being a boxy peanut bulge. You can even kind of see the X shape in the Milky Way, and it also has a cylindrical rotation, which means that the line of sight velocity is independent of height above the plane, and this is characteristic of boxy peanut bulges. However, things get a little bit more complicated when we go and look at the chemistry of stars in the bulge. And here I'm showing you, this is for one field in the bulge. And this is showing you the metallicity of stars in this field. And as you can see, there's a really broad range of metallicities. And this points to the coexistence of multiple stellar populations in the bulge. Now, there's a rather broad consensus in the community that these metal-rich populations are part of the disk. So they're part of the bar, and they also participate in the boxy peanut bulge. However, there's been more of a debate about what the origin of these metal core populations is. And the kind of two main scenarios, I would say, is that these populations are part of a dispersion-dominated spheroid, so a classical bulge. So in this case, the Milky Way would have a composite bulge, let's say, both a pseudobulge and also partially a classical bulge. And then the other scenario is that these metal pore populations are just part of the thick disk that we see at the solar vicinity, but just extended into the inner regions of the Milky Way. So if in this scenario, there's really no room for anything else in the bulge apart for just kind of thin and thick disks, or a pure disk scenario for the bulge. So to explore this scenario, back when I was in Paris, what we did was we used isolated simulations that we tailored to the Milky Way to ask the question, can we reproduce the properties of the Milky Way bulge just with a pure thin and thick disk population? So a pure disk scenario. So to do this, schematically, I'm showing you here how we did this. So if you go, what we did was to look at the stellar populations in the disk of the Milky Way. This is from the nice work of Bovie et al. And if you look at these different monoabundance populations, which is each of these points here, what we see in the disk of the Milky Way is that the vertical scale height, which is what you see on the y-axis, and on the x-axis, you have the radial scale length. So you see that metal pore populations, which are these blue ones up here, so the color is metallicity, have a large scale height and a short scale length. And you have this continuum towards more and more thin populations, so that have smaller scale heights and that have larger scale lengths. So what we did was to create an n-body model where we discretized this into 3 populations because it was just easier to do this. But these 3 populations have scale lengths, scale heights, kinematics, and metallicities and alpha abundances that correspond to a kind of discretized version of the Milky Way. And what we did was to set the masses of these populations according to this a star formation history derived by Snaith et al. In 2014, which basically means that what we did was that we set these 2 populations to have 50% of the mass, and the other 50% of the mass is in the thin disk. So the thick and intermediate disk in our models is very massive. It's half the stellar mass. So then we run this n-body simulation. We let it evolve self-consistently. It forms a bar and a boxy peanut bulge. And then we go and we just observe this in the same way that we would observe the bulge of the Milky Way to try and understand if we can reproduce these properties. So can we reproduce the morphology, the kinematics, and the chemistry in such a model? So what we found in these studies was that if we separate out the cold and the hot population at the end of the simulation, what we found interestingly was that the cold population has a much stronger, kind of more prominent bar strength, and also the peanut shape is much more prominent if we compare to the hot population. And this was also found in de Baptiste et al. 2017, who named this kinematic fractionation, which essentially means that the morphology of these components is really dependent on the initial velocity dispersion of each of these populations. And why this is interesting is because if we take cuts now along the major axis of these models, so similar to how we observe the Milky Way, and we look at the density distribution, we find the following. So now you're looking along the x-axis, this is along the major axis of the bar, and this is the density of stars for the cold in blue and the hot in red. And close to the plane, what you see is just one peak, which corresponds just to the density peak, in the center of the disk. As you move further away from the plane, you see in the cold population, you see these 2 peaks, while in the hot population, you see this 1 peak. And that's because, as I was showing you, the peanut shape is much stronger in the cold population compared to the hot population. And then as you move even further away from the plane, you have this very strong double peak in the cold population, and you start to see it in the hot population. And why this is interesting is because we were seeing similar things also for the observations. So here, this is from the work of Rojas Arriagada et al. And he separated stars into the metal poor, which is, metal rich, which is the gray, and the metal poor, which is the blue. This also corresponds to the cold and hot population. And you can think of this as a proxy of distance along the line of sight. And you can see that close to the plane, you have these single peaks in both populations. As you move further away from the plane, you start having this double peak in the cold metal rich population, but you do not see this in the hot metal poor population. And as you move even further away from the plane, you have this very strong double peak in the cold population, and a hint of perhaps a double peak, although this is very tentative, in the metal poor hot population. So this can help us understand why, if we have such a scenario, why we don't see a double peak also in the metal poor population, but we see it much more prominently in the metal rich population. So we find kind of similar trends in morphology for this cold hot populations, which correspond to the thin and the thick disk, as we see also in the Milky Way bulge. If we go and look at the chemistry now, so what I'm showing you is a metallicity map. So this is galactic longitude versus galactic latitude, and the color coding is metallicity. So this is the kind of metallicity map that this thin plus thick disk model would produce. And the reason we have this metallicity map where you have close to the plane, you have high metallicity, this is because the metal-rich population is dominating close to the plane. So this is color-coded, showing you the surface density fraction. So light colors here shows you a high fraction for this population. And you see that further away from the plane, the metal-poor population, which is shown down here, at high latitudes, the metal-poor population dominates. So this is why you have also this gradient, vertical gradient in metallicity in the Milky Way. Now, if we go and compare to what we see in the data, for example, in apogee, so this is what's shown in this middle panel here, and on the bottom, this is the model convolved with a distance distribution function, the apogee distance distribution function, so to match the data, to match a bit the selection function of apogee, basically. And what you see is that the model reproduces quite well what we see in apogee. So you have this metal-rich disk, this metal-poor inner population here, or intermediate population, and then this metal-poor population at large heights above the plane. And the same for the alpha abundances, you match quite well what we see in the observations. And I just want to reiterate that this is not a fit of the model to the data. This is just an n-body simulation that has the properties of the disk of the Milky Way, and then we see what we get out in the bulge. This is not fit to match the data. Also, if we now go and actually look in each of these regions and actually look at the distribution of metallicity, so the metallicity distribution function, rather than the average value, this is what we would get. So each of these panels shows you a given region in the galactic bulge and kind of moving towards the disk. So this is in the center, and this is moving out to the disk, and this is moving to larger latitudes. And the red histograms are showing you the data from apogee, and the blue is showing you, the blue lines show you the model. And you see that we match, that this matches quite well what we see in the data, in the sense that you have these two populations, this metal-rich and metal-poor population, and the central regions. As you move out towards the disk, the metal-rich population dominates more. As you move further away from the plane, the metal-poor population dominates more as well. So in this study where we looked at isolated simulations that were tailored to the Milky Way and had a thin and a thick disk, we found that we could actually reproduce the morphology, also the kinematics. I didn't go into this because I didn't have enough time, and the chemistry as well of the bulge of the Milky Way, and I put some references here. So because all of this therefore seems to hint that we can actually reproduce what we see in the bulge of the Milky Way with just a thin and a thick disk, and this hints to an in situ or disk origin for the Milky Way bulge. However, the question is, of course, can we reproduce such a pure disk formation scenario in the lambdaCDM cosmological context, where we know, of course, that mergers are very important, and so we expect massive galaxies to undergo a large number of mergers, and so we expect there to be an ex situ component in the bulge of the galaxy. So to study this, we used the Auriga simulations, which are a suite of 30 high resolution zoom-in simulations that have a comprehensive galaxy formation model with star formation, stellar feedback, AGN feedback, et cetera, that form these very nice barred galaxies. So you can see, if I fast forward a little bit here, by redshift 0, you have these very realistic looking barred spiral galaxy. So what we did here, one of the things that we looked at is the chemokinetic properties of the simulations and compared this to the Milky Way. So what I'm showing you here is line of sight velocity on the top panel and velocity dispersion as a function of galactic longitude. And first I'm plotting here, this is for the Milky Way, this is the data. So this, in the different colors, I'm showing you stars with metallicities above 0, with intermediate metallicities and low metallicities. And this is from the Argos survey from Ness et al. And what you can see is that in green, the metal-poor populations have very similar line of sight velocity to the metal-rich population, which is the red. Even though the metal-poor population has a higher velocity dispersion, is much hotter. So if we go and now observe one of these cosmological simulations the same way we observe the Milky Way, etc., and do a similar kind of analysis, what we find in this one case, so this is for this galaxy Auriga 18, in this case we find similar-ish trends. So we find that this green line, which is the metal poor population, is similar to the more metal-rich populations, even though there's a higher velocity dispersion. However, in this other case here, now this is another galaxy, this is Auriga 26, so it has a completely different merger history. Here we see that the green line is very different. So the metal poor population rotates much more slowly than the metal-rich population, and it also has high velocity dispersion. So what we found was that the metal poor component has very different properties depending on the Halos formation history. And how we quantified this was by taking this difference between the metal-rich and the metal poor populations at the edges of the bulge. And we were able to find, so this is what's plotted on the y-axis, so this is for all the Auriga galaxies. And on the x-axis, this is a proxy for how much impact the mergers have had. So it takes into account all the mergers and at which redshift they happened and the mass ratio of the merger. So on the right, you have kind of more mergers that have had a larger impact that have happened at lower redshift. And in this case, you see that you have a big difference between the velocity of the metal-rich and metal-poor component. And on the left, you have fewer mergers. So very few mergers, and that happened very early on. So what we find is that the most quiescent galaxies in Auriga, the ones down here, are actually those that have similar the most similar properties to the Milky Way. So the Milky Way, the difference between the metal-rich and the metal-poor component, if you remember, is very small. So it lies down here somewhere. So this implies that the Milky Way's formation history is very quiescent and that it really makes up the tail of the distribution. And so that it hasn't had many mergers. And in fact, from our models, from the Auriga simulations, what we find is that the last major merger must have happened more than 12 gigayears ago. And so this also puts constraints on the mass ratio of mergers such as the Gaia Enceladus sausage merger, that it can't have been more massive than a 1 to 20 merger. Now, if we go and look at these, at the fraction of in situ versus ex situ stars in the bulge, this is what I'm showing here. So this is for 5 of the galaxies in Auriga. And so these 2 galaxies here are the ones that have the most similar chemodynamic properties to Auriga. And we find that these have a very low ex situ fraction. So less than 1% of the stars, which is, so the ex situ fraction is shown in red, less than 1% of the stars are formed ex situ inside the bulge. So these galaxies that are most like the Milky Way really have a bulge that's formed essentially in situ. So the takeaway message from this is that the Milky Way has had a very quiescent merger history and really has a primarily in situ bulge. And this is compatible with other studies that have looked at this, but not looking at the bulge, but using different techniques to explore the merger history of the Milky Way. So the next point I want to touch upon is on the impact of bars on Milky Way type galaxies. So as I'm sure you all know, when Gaia DO2 came out a few years ago, we were all flabbergasted by the just very rich substructure that was seen in the data. So here, what I'm showing you is the tangential velocity as a function of radial velocity, where you can see that there are these very prominent ridges in this plane. This was shown by Kawata et al. In 2018, just after the second Gaia data release. When we look at these substructures in the V-phi-R plane, but we color code by radial velocity, so the velocity with which stars move in and out in radius, we also see a lot of substructure here as well. So one of the things that we wanted to do, we went and looked at, was to see if we can connect any of these substructures to the orbital structure that's induced by the bar. So we know, as I said, that the bar is going to induce some kind of substructure. So we wanted to go and see if we could connect this to the bar using some n-body simulations. So what I'm showing you here, this is for the same simulation I was showing you before. And this is now showing you the tangential velocity is a function of radius. And I'm going to let this run. So this is the initial conditions, and then you see what happens once the bar forms. And you see that it's very messy. There's a lot of substructure here. There's a lot of things moving around. But you see that after about a gigayear, the bar is kind of rotating quite steadily. And what you see is that there's this very prominent long ridge that's formed, and that is quite stable in the sense that it's always there. You can always see it. And this is formed really in the outer disk of the galaxy. So what we wanted to do was to go and explore what this very long ridge is made up of. So we carried out in this simulation, we went and explored the frequencies of stars in this ridge. And what we found is that essentially the stars that make up the ridge are predominantly trapped at the outer limblad resonance. So we found that the longest ridge is really made up of stars that are trapped at the OLR of the bar. And this longest ridge is also created by the bar outer limblad resonance, is also, you can see it also if you look at axisymmetric action space, as was shown nicely by this work by Wilma-Trick. And also what's really nice in action space is that this line here, which denotes where the outer limblad resonance is, and you can see that there's this ridge just to the right of it. This line also falls perfectly between an inwards and outwards moving feature in radial velocity, which is very, very interesting as well. And we also went and calculated the closed periodic orbits in this n-body simulation that I was showing you before. And we found that these closed periodic orbits are also associated to this large ridge. The closed periodic orbits that are associated to the outer limblad resonance, so this X11 and X12 orbits also lie in this region where this very long prominent ridge is. And we also studied this in cosmological simulations, in the Auriga cosmological simulations, because of course, what I was showing you before is just one galaxy, it's one simulation that's in quite, let's say, idealized conditions. So we wanted to see if we would get something similar if we went and looked at cosmological simulations, which are much messier, and there's a lot of other substructures there as well. And what we found is that in at least the simulations that look a lot like the Milky Way, we have this long ridge which is associated to the OLR. So the dashed line shows you the location of the OLR. And so it seems that this long ridge it generally tends to be associated with the outer limblad resonance as well, also in the cosmological simulations. So that's cool, because if we find the longest ridge, and we know that it's consistently produced by the bar OLR, a caveat here is that if you had a very important interaction going on, then this could mess things up. But in principle, you could use this to constrain the bar pattern speed if you can isolate this ridge. So the other thing that I mentioned in the beginning, is, as you might remember, is that bars can push gas to the central regions, and there they can form these nuclear structures. So what's very interesting is that we have more and more kind of evidence for these structures. This is from news data from the Timer survey, which is a survey of 21 galaxies, where we've been exploring the central regions of barred galaxies. And what you can see is that in this case here, NGC 1300, in the inner region of the galaxy, we see this very highly rotating component. So this is line of sight velocity here. And on the right here, this is the stellar velocity dispersion. And you see that there's a big drop in stellar velocity dispersion in this region as well here. And if you look at H3, you see also that there's an anti-correlation between H3 and the line of sight velocity, which also indicates circular orbits. So we really see, and we found this in almost all of the galaxies that we looked at in Timer, this very highly rotating structure in the inner region, which really points to this nuclear disks that the bar is forming And we found really nice correlations between the sizes of these disks and the bar as well. So all of this is consistent with being formed due to the bar. And also we looked at the age and metallicity gradients of these disks, and we can find radial gradients inside these disks that point to the fact that these disks are actually forming inside out, similarly to the way that the main disk of the galaxy forms. And this is interesting because we can also see these kinds of things happening in simulation. So this is now an isolated simulation with gas, star formation and feedback that forms a bar. So here, what I'm showing you is the gas density, surface density, and the gas temperature. And a bar has formed, and you can see that you have these nice dust lanes forming, and also this pileup of gas in the central regions here, which is cold. And we've done some analysis that shows that these structures really grow with time, become larger with time. So we see this inside out formation as well. Okay, and the last point I want to make is on how we can use the dynamics of bars to study the dark matter content of barred galaxies. So as I mentioned in the beginning of the talk, if we embed a barred galaxy inside a dark matter, a massive dark matter halo, the bar can be slowed down due to dynamical friction from the dark matter halo. Now, when we look at a disk galaxy and we look at the angular frequency of stars as a function of radius, if there's a bar that has a given pattern speed, there will be there's a radius at which stars in the disk co-rotate, have the same angular frequency as the bar, and this is called the corrotation radius of the galaxy. Now, if you have a bar that's rotating that gets slowed down by dynamical friction from a dark matter halo, what happens is that the pattern speed is decreased, and this will mean that your corrotation radius will move outwards. However, we think that the dynamical friction doesn't affect the radius of the bar in any significant way. And therefore, what would happen in this scenario is that the ratio of the corrotation radius to the bar length, which is given by this, often is given by this squiggly r, will increase. So this is interesting because it means you can go and try and measure this squiggly r in observed galaxies to try and understand how much dynamical friction has been inflicted on barred galaxies. This is just a bit more from the theoretical side. So this was shown, this was work done by Victor Batista and Jerry Selwood, who looked at simulations to explore this, and what they are showing here. So this is on the x-axis, you have the kind of the baryon dominance of the simulation. So this is given by, if you look at the rotation curve, you can take the disk over the contribution of the disk over the dark matter, for example, to see how baryon dominated the system is. And on the y-axis, what they're plotting is this squiggly r, so the corrotation radius over the bar radius, this ratio. And what they found is that indeed, if you have very baryon dominated systems, you have this ratio is low. And as you have more and more dark matter dominated systems, then this ratio increases. This is often plotted in this kind of plane. So here you have the corrotation radius on the y-axis and the bar length on the x-axis, and kind of empirically, a lot of studies take this value of 1.4 of the ratio of the corrotation radius to the bar length as being a kind of value above which you would say a bar is slow, and below which you would say a bar is fast. So this is what the observations have found. So this is not a trivial thing to do observationally. It's not easy to get the bar pattern speed and then subsequently the corrotation radius. But there have been some studies that have found that bars are generally fast. So they lie below this line. So this means there's not been much of an effect of dynamical friction on barred galaxies. From the theoretical side, from cosmological simulations, this had not been looked at much before, but in the last few years, this has started to be explored. And in particular, there were two studies until recently looking at Eagle and Illustris. So this is from the work of Al Gori et al. And Peshkin et al., who explored this. And both these studies found that this ratio is very large. So this is now in the same plot I was showing you before, but in log scale. And this is where their galaxies end up at redshift 0. And also Pashkin et al. Found that you have, a large range of values, but this ratio is much larger than 1. So these would fall, somewhere above here, which is obviously inconsistent with what is seen in the observations. And recently, there's also been a couple more studies that I just want to briefly mention. So there's also this study by Roshan et al. In 2021, who looked at this in TNG 100 and TNG 50. And they also found that this ratio is much larger in the simulated galaxies than in the observed galaxies. And there's also very recently been a nice work by Francesca Fragkoudi, who looked at this in TNG 50 and did a very accurate comparison to bars in manga, and did not find as much of an inconsistency as Roshan et al. Found, but also found that in TNG, this ratio is larger than in observed galaxies. So all of this kind of, shows that we're not finding what the observations are finding, which raises the question, are fast bars incompatible with lambdaCDM? So we went to explore this looking at bars in Auriga. We started this work a couple of years ago. And this is what we found. So these colored points are what we found for Auriga. So I was very surprised to see that bars in Auriga actually are quite compatible with what we see in observations. So, and if you look at the ratio here, Auriga falls below this 1.4 value, which is not what we were finding, what other studies were finding in Eagle and Illustris. So of course we were asked ourselves, why are bars in Auriga faster than in other cosmological simulations? So we looked at a number of things, and I'll just go through these quickly, but one of the things we looked at was resolution. And we found that indeed, if we make our resolution worse to match what was found in Eagle and Illustris, we could get slightly slower bars, but this didn't seem to be enough to explain what we see in Eagle and Illustris. So these are our low resolution runs, and you see that they have slightly larger values than the high resolution runs, but this really doesn't match, doesn't compensate for what we see in the other simulations. And we looked at a number of other things, and none of these seem to be important enough to really induce this big difference. So what we did find is that if we look at the baryon dominance of Auriga galaxies, so if we, in particular, if we look at the contribution to the rotation curve of stars divided by the total rotation curve, so this is what I'm showing you here as a function of radius, the red line shows what we get in Auriga, and the green and purple line are what was found in Eagle and Illustris. So what we see is that in Auriga, galaxies are more baryon dominated. And this makes sense in terms of what we know from theory, because of course, if you have a more baryon dominated galaxy, you'll have less of an effect of dynamical friction. Interestingly, what happens is that if in order for Auriga to be more baryon dominated, this also means that the Auriga galaxies lie above the other simulations in terms of the M star M halo relation. So this is, the red line is the Auriga galaxies, and green is Illustris and purple is Eagle again. So you see that Auriga has higher stellar mass for a given halo mass, and this also lies above the abundance matching relation that's given by most studies. And if we look at this parameter here, which is the stellar mass over the baryon fraction times the halo mass, which is kind of a global star formation efficiency, if you will, Auriga also lies above Illustris and Eagle. Interestingly, there's been some recent studies by Posti et al. Who looked at observed galaxies and did some dynamical modeling to get their halo mass. And these are these points that I'm showing you here from the spark sample. And they also found that these massive spirals, so these are all massive spirals from this observational study by Posti et al., they lie above the abundance matching relation as well. So there seems to be some evidence that barred galaxies should be baryon dominated, and they should lie above the abundance matching relation to have dynamical properties that are consistent with observed bars. There's been hints of this before. So this is from some dynamical modeling that was done for the Milky Way by Bovie and Rix, who found that the Milky Way is very baryon dominated. So you have a large contribution from the disk of the Milky Way. And if you compare now, so if you compare this now with illustrious TNG 100, this is what's shown, this is right from the nice work from Lovell et al. In 2018. So if this halo for the Milky Way is given by this line here, and the average kind of halo circular velocity from TNG 100 galaxies is given by this green line here. So you see that the halos in dark matter halos in TNG 100 are more massive and more concentrated than what we see in the Milky Way. So there's been some clues that cosmological simulations are producing massive spirals that are not as baryon dominated as a lot of dynamical models suggest. And there's other studies also suggesting that these massive spirals are baryon dominated. And I just wanted to point out that we see this already from higher redshifts. So already from redshift 0.5, the Auriga galaxies are more baryon dominated. And just very quickly, how can we reconcile this with abundance matching? So Lorenzo Posti had this nice work that I told you about in 2019, where he showed that massive spirals lie above the abundance matching relation. And he recently showed that if you go and look at early type spirals, and he did some dynamical modeling, these seem to lie below the abundance matching relation. So this seems to suggest that the average value of the abundance matching relation still holds, but you have this very morphology dependent splitting of where galaxies lie, depending on if they're spirals or early type, which I think is quite interesting. So I think I'm out of time, and I just want to give you my take-home messages. So on the formation of the Milky Way, what we see is that what these models are telling us is the Milky Way has had a very quiescent merger history, where the last major merger must have taken place above redshift 3.5, and that the inner regions of the Milky Way, so the bulge, are really formed in situ. In terms of how bars impact Milky Way type galaxies, we see that the outer limblad resonance really creates a very long ridge in the V phi R plane, and we could maybe possibly use this to constrain the Milky Way bar's pattern speed. And there's a lot of accumulating evidence, both from observations and simulations, that bars can really efficiently form these highly rotating nuclear structures that we see in the central regions of galaxies. And that barred galaxies, in terms of the dark matter content of barred galaxies, we see that barred galaxies need to be baryon dominated in cosmological simulations in order to match the observed dynamical properties of barred galaxies. And this means that they have to be offset from the abundance matching relation as well. So thank you for your attention, and take any questions.
Thank you very much. That's amazingly rich phenomenology and access to physical processes through these bars. That's a real eye-opener. Thank you very much for that, and also for the pedagogical introduction. I'm sure there'll be questions. So I see already, no, I don't see. Well, while somebody's waiting, I just want to ask you about the dark matter probe. Mm-hmm. I mean, of course, you do get a good idea of the radial profile of dark matter from the rotation curves. Mm-hmm. Presumably, the dynamical friction will depend also more on the vertical extent and also on the granularity of the dark matter. I mean, is that something you are considering as well?
Yeah, it will definitely depend on those things as well, but that's not something that we've yet started exploring. No, I mean, but it's definitely important to, I mean, the vertical extent and how concentrated the dark matter is within, let's say, the bar radius will also be important, but we haven't started looking at that yet. No,
because I guess that we don't have an awful lot of empirical information on the vertical extent of the dark matter right in the middle of the galaxy. I mean, we have quite a lot here, you know, in the outer disk, but not in the middle. Okay, Andreas just has a question.
Yes, so thank you very much, Francesca. It was a very nice overview. Interested also in this dark matter dominated fraction. You have looked only on barred galaxy. What about unbarred galaxies? Are they in the same way dark matter dominated or not in the inner part? Or could it be that the unbarred, that just those galaxies which are pushing the Moster relation down are the unbarred ones, or something like that?
They don't seem to. I mean, this really big difference between falling like really above and below the relation seems to be, I mean, this really seems to be the early type galaxies, but we do, so we did not find that the unbarred galaxies fall below the relation, but we do find some offset, some difference between the barred and unbarred, but the unbarred do not fall necessarily below the relation, the abundance matching relation.
Okay, thank you. I have another small question about the Milky Way. Maybe I missed it, about this in situ bulge of the Milky Way. What is the mass of this in situ bulge component?
Well, it depends how you want to define the bulge.
I just want to see this kind of connection. If you look to the very center of the galaxy, we see this cuspy structure, yeah? Which is not the pseudo bulge. Yeah? And there's a long discussion now, is that relevant for the total mass of the inner galaxy or not? This kind of in situ bulge.
The nuclear, you mean the nuclear disk of the Milky Way? So in our model,
no, just if you're just looking on the mass in a kiloparsec, yeah, with this cusp structure and the stellar density of with a power law of minus 1.7, 1.8, yeah, which cannot be a disk structure. Yeah, but there's a big discussion about how much mass is there in this component, which I would call the in situ bulge.
So I mean, in our model, the mass of these two components here, which would be the intermediate and kind of a thicker disk component, which have a very short scale length also, so about 2 kiloparsec scale length. These two together have 50% of the stellar mass. So if you take your favorite estimate for the stellar mass of the Milky Way, this would be about half of that.
Okay, thank you.
Yeah.
Okay, I think we have time for one more question. Other people can also pose questions in the extended Zoom session after the end of the formal colloquium. So, I mean, Sebastian, please go ahead.
Thank you, Richard, and thank you, Francesca, for such a nice talk. I was quite intrigued by the second part about the stellar to halo mass relation and how it relates, how disks are different from early type galaxies, which is what I think your work also implies, along with the rotation curves and all the other dynamical studies. So I was just looking back at this paper from Ben Moster, where he also does this splitting. And indeed, you see that separation between early and late types. And he argues that this, because of the scatter, this depends on how you look at things. So observational samples are usually selected by stellar mass, and therefore you see what you see. But if you look as a function of halo mass, at fixed halo mass, spirals actually are baryon poor. And so I'm wondering if you have looked into this, because in your left plot here, you're looking at things as a function of halo mass, and it seems that the Auriga simulations are baryon rich. But what Ben Moster's interpretation is that it should actually be the other way around to make things work.
So yeah, so I mean, this difference in morphology, I think, as you say, has been kind of pointed out before between the early types and the late types in the M star M halo relation. But I think, to my understanding on this topic, this work by Lorenzo Posti, what he showed is that it's really the splitting is, let's say, much bigger than perhaps previously thought. So from my understanding, the split was kind of, you had a slight offset between the two, but here you really see that that the early type population really falls below the abundance matching, and the late types really kind of continue moving upwards to when you go to higher stellar masses. In terms of what you said about the late types being more baryon poor in the abundance matching, I mean, I'm not sure. I mean, well, that's not what at least the dynamic seems to be pointing to in terms of the bar dynamics. So that, if you want to, it seems that if you want to have bars that have the right dynamical properties, they need to be baryon dominated, and our model suggests that they need to lie above the abundance matching relation. So I'm not sure how to reconcile that with abundance matching predictions, which say that they are more baryon poor, I think is what you said, right?
Yeah, well, yeah, it's a subtle issue because it depends on how you select the sample. So I guess maybe that comparison can be done in more detail. And that...
Yeah, probably. I mean, this is still early stuff, and we haven't gone into much detail about morphology and how exactly you would separate these, but definitely something to look into more later.
Thank you. It's very interesting.
Thanks.
Okay, thank you. So before we thank Francesca, I just want to share the screen to make an announcement for next week's colloquium. Are you? Yeah, I hope people can see that. So next week we'll for the last colloquium in the series, we'll go back to the world of high energy astronomy, and we will hear from a figure very familiar to many of us here in Heidelberg, who will give us the benefit of his experience in this field and what the latest research is showing about the origin of cosmic rays. So that's next week, and I will just invite everybody now to open up their screens and open up their microphones, and let's give Francesca a really great send-off, because that was a really interesting colloquium. Thank you very much.